Hi, I'm Ben Wormuth. I'm the team lead for the George Washington University rocket team. This year, we're presenting our rocket, Skyfall, and our payload, MARCO-POLO. The GW rocket team has about 30 student members, 4 captains, and myself as team lead. We have 4 sub-teams: aerostructures, recovery, payload, and propulsion. 12 of our members over this year and the past year are level 1 NAR certified, and we're competing in the 10,000K SRAD competition this year. Our team is split across many different genders and majors in the School of Engineering and Applied Sciences here at GW.
Hi, I'm Adam. I am the captain of the aerostructures team here at GW, and we did a lot of the design work for our rocket using OpenRocket. We designed our rocket to have a apogee of around 10,000 feet, but putting in all the values into OpenRocket, we found out that our expected apogee was around 11,000 feet. The expected velocity off the rail was about 114 feet per second, with an expected max velocity of 0.93 Mach and an expected max acceleration of 421 feet per second squared. Our rocket had a stability of 3.18 calipers, which is right in the range where we would want it. And when we actually got around to building the rocket, we used fiberglass because it's a really strong material that is also radio transparent, which is perfect for what we're looking for. And the total rocket composition is 3 fins, 3 couplers, 3 body tubes, and a nose cone. Like I said, all made of fiberglass. The total length of the rocket was about 13 feet tall, a total weight of 81.5 pounds, including the motor. As you can see in the bottom, that is our open rocket simulation graph with vertical motion versus time, and you can see the expected apogee of a bit over 11,000 feet and the max velocity there in that graph as well.
The propellant that we're using this year is an AP-based propellant with HTPB, and it has a total impulse of just over 12,000 Newton seconds, burn time just above 3 seconds. It uses 6 grains in a 40-inch aluminum tube with a graphite de Laval nozzle. This propellant was used previously for a couple of years. We really like how it comes together, and it's very easy to work with. Our static fire, you can see in the picture there, this is a successful static fire. It confirmed everything that we expected to see. You can also see our propellant formula characterization data down there on the graph. You can see it has a high percentage of aluminum and AP in there. Also copper oxide.
Hi, my name is Ariana Lesniak, and I'm the recovery captain for the GW rocket team. Our recovery system for Skyfall this year was a standard dual deployment method. We had a 12-foot main chute that was made out of nylon. We had a 6-gram and 8-gram black powder charges, the 8-gram being the backup charge. Our main parachute was deployed at 11,000 feet with a backup at 1,000 feet. Our drogue was a 3-foot Kevlar drogue with 4 grams and 6-gram black powder charges, the 6 grams being the backup charge, and that was deployed at apogee with a backup at 1 second after apogee. Our 2 altimeters we used for redundancy purposes was the Altris Metro Easy Mini, which was our backup altimeter, and then our Perfect Flight Stratologger, which is our main altimeter.
Hi everyone, my name is True Jackson and I was in charge of designing, building, and testing this year's payload MARCO-POLO. Put simply, MARCO-POLO is a low size, weight, power, and cost laser communication demonstration for small satellite applications. The upper and lower halves, named MARCO and POLO respectively, have electronic systems that operate completely independent of one another. This decision was made to simulate laser communication between 2 independent satellites. The only physical connections linking MARCO and POLO are 3 strands of 9-inch aircraft cable, each attached to a pair of eye bolts. These allow MARCO and POLO to be separated by 10 inches during descent under parachute, with MARCO free to move relative to POLO. To correct for this movement, the team designed, manufactured, and tested a laser gimbal that uses pitch yaw actuation to aim a 25 milliwatt, 650 nanometer wavelength laser. This laser uses TTL modulation to transmit timing data from POLO to MARCO which is received by a team-designed and assembled photodiode receiver with heightened sensitivity in the red light spectrum. Testing with the finished array yielded readings of 280 to 300 millivolts when placed outdoors in the middle of the afternoon, and readings of 400 millivolts with the laser beam focused on a photodiode of the array. To convert the voltage spikes created by the laser back to their corresponding UART signal, the team tested and finalized a Schmidt-Traeger circuit that cleans the data from the receiver in a single filtering stage. After implementation, the team tested performance when the laser and receiver were stationary and separated by a distance of several feet. Under these conditions, the receiver was able to correctly read back 100% of characters sent over using the laser beam. To control the movements of the gimbal and keep the laser beam focused on the MARCO receiver during descent under parachute, a vision tracking software was created and executed off of an ARPI-0W. The software analyzed a continuous stream of images gathered by an ARPI camera mounted to the top of Polo with a direct line of sight to the bottom of MARCO. Each image was processed using a color thresholding algorithm to isolate the portion of the bottom plate of MARCO that was visible in the frame and determine the pixel centroid of that portion. Correlation tests then define the relationship between the pixel centroids and the serval angles that focus the laser beam on the center of MARCO's receiver at that instant in time. Once these relationships were hard-coded into the vision software, full-scale ground tests were run to characterize the performance of the laser communication system under pseudo-flight conditions. These tests revealed that only pairs of characters could be read back successfully at a time when Polo experienced high jerk relative to MARCO. The Polo TC microcontroller was then reconfigured to send the 8 digits of a timestamp digit by digit in a cycle that repeated every 0.4 seconds. The MARCO TC would then record readings for each of the 8 digits and use them to reconstruct the full timestamp. These timestamps were represented as the offset in milliseconds between the MARCO TC timer and Polo TC timer. All data related to these offset calculations and periodic transmission stats are saved to an SD on MARCO along with acceleration, orientation, and ambient reading data. After these reconfigurations, final ground tests of the payload yielded the following data. Phoenix Price, who was in charge of designing the photodiode array and performing characterization tests with it, will explain these data in further detail.
Hi everyone. The first paragraph here shows a histogram of the offsets logged and calculated on MARCO while MARCO-POLO sat inside the rocket before the launch in April. Of 170 offsets obtained, 83% fall within 2 standard deviations of the mean estimated offset of 8.55 seconds. This compares well to the offset value of 8.71 seconds obtained from timing the MARCO and POLO arming events with a phone stopwatch. This data verifies that digit-by-digit transmission can be used to reconstruct the offset time between MARCO and POLO with a high degree of accuracy. Although using independent digits to reconstruct the time produces variation between offset measurements, simple statistical analysis allows for reliable offset to still be calculated from a small sample of estimates. The second graph shows transmission statistics calculated after every 4 seconds of a 6-minute ground test, which was performed before the April launch date under pseudo-flight conditions. The test was conducted in the middle of the afternoon with the parachute hung above the payload in full view of the camera, with active tracking and gimbaling during the entirety of the test, and with the payload subjected to moderate shaking throughout. 3 percentages are shown on the graph. The first, shown in blue, lists the percentage of characters received by MARCO compared to the number of characters expected under ideal conditions. The team identified ideal conditions as those when MARCO had no relative velocity or acceleration compared to POLO, and the laser beam was focused on a photodiode, which produced a throughput of 200 characters per second. The second, shown in orange, lists the percentage of correct character readings compared to the total number of characters received. Incorrect characters are read when the laser beam moves off the array or onto a dead spot of the array as a character is being transmitted. These 2 percentages, when multiplied together, produce the effective transmission percentage shown in green. This is the percentage of usable information received compared to the amount expected under ideal conditions. When compared with the lateral acceleration data recorded during the test, the team came up with 2 major conclusions. First, when MARCO experienced nearly constant non-zero acceleration, 80% of characters were received compared to ideal conditions, with half of these being correctly read for a transmission performance of 40%. Second, when MARCO experienced high jerk, 45% of characters were received, with about the same percentage being correctly read for a total transmission performance of 20%. The high percentages in blue shown during periods of constant acceleration would not be possible without the visual tracking software designed by the team. I'll have Mark Yamakaitis, who tested out multiple tracking methods and produced the final tracking algorithm, explain some of the software and calibration in greater detail.
Hello, everyone. The different stages of our final color thresholding algorithm are shown in the following figure for a single camera frame. First, the original image is retrieved from the camera and split into the image's blue, green, and red channels. Arithmetic operations are performed independently on each channel to brighten up the background before the channels are rejoined to create a grayscale image. This image is then converted to a binary image using OXU binarization and inverted in a single step using OpenCV functions. The resulting binary image is then run through two morphological transformations in series to remove noise from both the background and plate sections. Through this process, even images retrieved under heavy shaking with a moving parachute and varying degrees of ambient brightness were all successfully transformed into a binary image as clean as the one shown here. We then extract the centroid of this region using the average index location. The following two graphs show the result of correlation testing. These were used to manually calibrate the centroid retrieved from an image with the corresponding servo angle pair on the gimbal. The results of manually calibrating 240 angle pairings are shown on the left, which demonstrate that each of the two servo angles do indeed operate along orthogonal axes. The pairings that were not tested are assigned the value of 0 and shown in dark purple. The relationship between observed centroid and servo angle was then plotted on the right, along with the two 7th degree polynomial functions to calculate the servo angles based on the centroid. These two functions are the ones that were hard-coded into the final visual tracking software. The team then added a predictive tracking element to the software to minimize lag between the position of the receiver and the position of the laser beam.
We started the year with a dual stage design, and we were able to test fly the sustainer of this dual stage design to test the deployment method of the payload. Unfortunately, due to a commercial off-the-shelf motor malfunction, we had a non-optimal flight, so we had to pivot for our test flight in April of Skyfall. We changed the dual stage design to a single stage design, and we had a beautiful flight up to 10,500 feet. However, we had a non-optimal recovery of this rocket.
This was a pretty tough year for the team. Campus was pretty much closed for all of our year. We had access for some students, myself, and one other student at a time. We were able to get about 8 students in total throughout the year to work on the rocket, and everyone else was able to connect in remotely. This made everything incredibly difficult, and this led to some of our errors and issues with our test flights. On the bright side, we built and flew 2 independent rockets. We had a lot of hands-on experience from those 8 students, as I mentioned. Our virtual participation means that we have a great knowledge base going into next year, and we had a big focus on data acquisition and reliable data logging, especially with payload. We've been able to pull some data from the flight that we hadn't done before, and we're going to actually roll this over into a flight computer for next year. So we're looking to come back with that flight computer, returning to work with really no knowledge lost over the pandemic. We're going to next year try to improve our system reliability, obviously, given some of our issues that we've had. Delegating additional responsibility to team members. This was quite a challenge given that we're virtual, and really it was myself and one other student at a time that were able to do tasks. We also are going to put a larger focus on system integration and how subsystems affect each other. There's a mindset of kind of being stuck in everything that you're doing, but incorporating all of that into a complex rocket is really challenging, and I think that's going to be a great thing for us to focus on next year.
We would like to end this presentation by acknowledging some of the faculty members at the George Washington University and some of our mentors outside of the university. We'd like to thank Dr. Murray Snyder and Dean John Locke for GW's support. We'd like to thank Ben and Elaine Russell, who are our mentors outside of the university. We'd also like to thank Bill and Tom, who are the machinists at GW. We'd also like to thank Ezra and the rocket community, who are allowing us to present and show the work we've done this year, even during these circumstances.